Here you'll see a bunch of paper clips swaying back and forth as they hang from a string. And there's a meter stick. Actually, I've got the inches showing rather than the meters. For reasons, well, because we need you to be able to read it. And if we had the centimeters there, you wouldn't be able to read anything. Now, let's just go ahead and zoom in on what we've got there, so we can follow the system. The string goes up to a pulley and across, and then down where it loses focus. We'll get the focus back, and I'm going to zoom back a little bit, show you the setup. Not a real high-tech setup, just a couple of chairs and a board across them with a pulley attached. Now on the other end of the wire, or the string, or the thread, which I can pull very easily as long as it's down in the water because of the buoyancy, is a glass Christmas tree ornament full of water with a hook around the end. And it's immersed in water. The weights that you saw hanging just counterbalance. The weight of the Christmas tree ornament in the water. Now the ornament is on the bottom of the container, I believe. I'm going to come over here and check it. Yeah, it won't go down any deeper. And you can see where the top of the hook is here, pretty close to the 22-inch mark. Okay, now if I pull this thing down, it'll just keep moving on its own, and it'll kind of bounce back up, and that's an interesting phenomenon. But if I pull it back down here, you see about how far it goes until the weight reaches the top of the water. Now if I add one paper clip, this balance is delicate enough, we're close enough to the balance, that the system will go down, well, the Christmas tree ornament will rise in the water, but this is the position where the Christmas tree ornament begins to come out of the water. There's a breeze in this room, and every time it acts up, we lose the meter stick. And you should note that position. Now what we're going to do is when the hook gets to, let's say, the 16-inch position, and it will, that's the end of the timing. And when it starts at, what is it, approximately 22.5-inch position with the ball on the bottom, of course that's when we're going to start the timing. Now I'm going to release this on a count of 3, and I want you to time it. Now I'm going to release it just by holding the pendulum still so that I don't give it any initial momentum. Okay, now you're going to time this. On 3, you start, and when we reach the 16-inch mark, you stop. Ready? 1, 2, 3. Okay, that's the acceleration we get from the mass of a single paper clip. Now we're going to add a second paper clip, and let's see what happens. I'm going to time it the same way. Let's stop some of the swaying here. We don't want a lot of swaying because there's a centripetal force involved with that circular motion, or that partial circle, and that's going to throw things off. So here we go again. Are you ready? 1, 2, 3. Okay, that happened a lot quicker, didn't it? Okay, we're going to do another. I get these paper clips separated. Bring the system back up. And we'll add a paper clip. Get the system nice and stationary. Ready? 1, 2, 3. Okay. We'll add a fourth paper clip. Ready? 1, 2, 3. You might ask yourself if we have simple harmonic motion or something close to it at the bottom. Okay, another paper clip. And 1, 2, 3. Another paper clip. And 1, 2, 3. Hope you're counting the paper clips. If I can get these paper clips apart, I'm going to add 2 paper clips this time. Matter of fact, let's do it like this. Running out of room to add paper clips. Ready? 1, 2, 3. Think of the motion. Of the Christmas tree ornament in the water. And one more. Ready? Just a minute. Ready? 1, 2, 3. Now what you need to do with the data that you've obtained is determine the average velocity versus the time. The average velocity versus the number of paper clips. The net force on the system is the weight on that number of paper clips. And each paper clip is approximately 1.2 grams. So you can determine the velocity, the average velocity of the system versus the number of paper clips.